Well, welcome everybody. This is John Siekmeyer here with MnROAD Office Materials. Welcome to the webinar. Today we have the chance to listen to Dr. David White from Ingios. David and his team spent several weeks this summer on the reconstruction at MnROAD, and today David is going to be speaking with us about the mapping that he did up there. So we're very grateful to Ingios, their partnership with the MnROAD group. And with that, I'd like David to start in. Thanks a lot. Have a good day.
Great. Thanks for the introduction, John. Just check, make sure you can hear me.
Yep. Yes.
All right, great. As John mentioned, we had the opportunity to participate some of the testing activities this summer as part of the low volume reconstruction. Today I'm going to talk about some of the validated intelligent compaction mapping results. I've highlighted here the locations of the testing that we were involved with. So each of the data sets I'll talk about has a unique cell number that's shown on this map. When we talk about cells 128 and 228, those were interesting because the outcome from the initial constructed resulted in conditions that were a bit softer than desired, so those sections were reconstructed. So that's highlighted here. We have results both on the original construction and then the reconstructed sections. Won't go through all the details here, but we've prepared a draft report that summarizes each of the different sections, the details. Just looking quickly here, the sections were comprised of different thicknesses of pavement foundation materials, different types of subgrade materials, and then also different pavement sections. Here's a summary of the different sections that we had the opportunity to do testing on. So if you look in the upper left here, for example, cell 424 had 6 inches of class 5 aggregate base over same subgrade. And then moving to the right, other sections we were able to map on the existing subgrade and base that was kind of recycled for that section. And then moving over to the far right, we had the opportunity to map the clay loam subgrade. Some of this was imported for this cell. And then also after the aggregate base layer was placed. And then there were just a variety of different sections. And bottom right, cell 127, 227 includes some of the large aggregate subbase sections. Parts of those sections had 18 inches of aggregate base. And then in the bottom left of this figure, some of them had 9 inches of large aggregate base. And those are the ones I highlighted earlier that required some reconstruction and incorporation of geosynthetics there to help stabilize the foundation. These are the details of that cell 228, 128, that was then rebuilt over intentionally wet, saturated subgrade conditions, where there ended up being 4 different subsections, 2 different geogrid products, and then also a non-woven separator fabric. So we were able to get some test results on those, which was, I think, interesting. When we thought about the type of testing that we wanted to do with the validated IC, we looked at the design approach that's being used by the different participating NRR states and those are listed out here. So we studied each state. We had to talk to pavement engineers in those states and come up with this simple table. Over to the far right, you'll see the design inputs for subgrade and also for base and subbase. What we ended up doing is focusing on the MR resilient modulus as part of the field verification program. And what that involved is field validating the intelligent compaction results in terms of resilient modulus outputs. You'll notice that some of the states use R value, IBR value, and also K value. CBR value is also in there. There's opportunities to develop these mapping outputs for other parameters, but we chose to focus on resilient modulus for the work that we were doing. Some of the tenets of field measurement that I think motivate the kind of work that we're doing are listed here. I just wanted to run through these 3 items. First, performance of pavements is directly coupled to the support provided by the foundation layers and embankment. I think everybody would agree on that. Second, pavement foundation layer stiffness, where stiffness is resistance to deformation in response to implied stress. Permanent deformation, which is deformation not recovered from removal of applied stress. And then uniformity of support, which deals with local variations, are all critical factors that need to be measured to verify construction quality. And then thirdly, if we can measure these critical engineering properties and understand how they affect performance, we can actually improve pavement design. So we have good inputs that do relate to performance. And then lastly, with improvements to design, pavement system performance can be optimized and risk of problems is reduced. So these 3 tenets are things that we think about when we want to develop a test program for evaluating site conditions. So at MnROAD, we deployed what's called the automated plate load test system. This system is designed to measure the in-situ stress-dependent resilient modulus for both aggregate base subgrade layers, and is also used to perform static testing that's normally used to for PCC design to get modulus subgrade reaction values. Most all of the testing we did here involved cyclic plate load testing from stresses on the order of about 3 PSI cyclic stress up to about 40 PSI. So we had a range of stresses that we used to evaluate the response of the different materials. Once we were able to complete the APLT testing, we then used that information to validate the intelligent compaction output and set up the machine to report the in-situ resilient modulus. These graphs show the statistical outcome from that regression analysis. If we just look at the upper left figure, this is the prediction model summary statistics at 10 psi cyclic stress. Our squared value is 0.95 and our measurement error is about 1,650 PCI. And that's over a range of about 10,000 to 35,000 PSI for resilient modulus. So once we have that information, we program the machine and then go about mapping these different layers and studying the resilient modulus response. The red dots here indicate the response for the base layer and then also the subgrade layer. The first graph that I showed, this blue line, is the composite response. And then, again, we isolate the base layer and then the subgrade as part of our output. So in the report for each of the different sections, there's a summary of the resilient modulus average, standard deviation, and coefficient variation for the different stress levels, including both composite, base, and subgrade. And it's interesting, I think, to go through and look at both the average values, how much variation there was in each section, and how the values change as a function of stress. So we won't go through all of these, but there's 3 summary tables that were developed for all the different sections. I want to spend a little bit of time on this plot because this helps visualize the information that's in that table. Each one of these plots represents a box plot for each of the different sections that we tested. And what the box plot shows, each of the data points there represents a measurement from the VIC system. The left endpoint represents the limit of the data on the left. The right vertical line represents the limit of the data on the high side. So from left to right, that axis is the composite resilient modulus in PSI. And then there's a box at the middle that shows the percentiles relative to the median value, which is the vertical line inside that box. So what we're looking for here is where's the position of the vertical line in the box. That gives us the median value, or it's close to the mean. And then what's the spread left and right of the data? That gives us a sense for the variability in that section. So if we look at the upper left, 124, 224, the median value is about 50,000 PSI. So that's a fairly stiff foundation. This is the one that had aggregate base over a sand subgrade. It was very stiff. But we also see that there's a fair bit of variability. Most of the data is sort of in the 30 to 70,000 PSI range. If we contrast that to 138, 238, we can see that the median value in 138 is on the order of about 7,000 PSI. Most of the data is in that 5 to 10,000 PSI range, but there is some scatter. There's a few isolated areas that show stiffer responses. So if you go through each of these different sections, you can kind of get a sense for how the average value and also the variability is changing with each of those different sections. In our report, we have these plots also for the base layer and also the subgrade independently. This is just the composite response, not looking at the layered values. So the reason that we did this is when we think about the different design approaches that each of your states are using, what we should be able to do now is for each one of those sections, go back to design with these resilient modulus numbers and go through a design prediction to see how well the eventual future performance relates back to what the design approach is right now. Hope that makes sense. So that's a little bit of background, gives you an overview for what we saw for the different sections that we tested. So what I want to do now is I'll go through and we'll look at some of the maps for each of the different sections. Before I do that, I want to just talk a little bit more about the data analysis process. And if Bob or John, if you could just tell me if you're seeing the website now.
Yeah.
Yeah.
All right. Thank you much. So, one of the things that it's been about a year now, we've been working on is developing methods to help state agencies and federal agencies deal with data and information that comes from intelligent compaction, but also just other inspection related to compaction. This is what we call our dashboard. So this is a system that we use to process all of the data in these maps, and I'll just highlight a couple of features here. There's 9 panels on this version. They're customizable depending on what the user needs are. But just going from left to right, there's what we call site vision. So if there's a webcam on the project, we pull that in. When we calibrate a machine, it's important to be able to validate that calibration is still valid for the materials that's tested. So we have some real-time analytics that tell us if the calibration is valid. What we're seeing is that, like at MnROAD, we've calibrated the machine to that site for those materials. As we add new materials, we can embed that within the calibration so that it just continues to become more robust over time. And then over to the right, there's an asset map. This just simply shows where the different machines are at. There's a quality analysis panel, and we've come up with 5 different key metrics that we think are important for compaction, pavement foundation, quality verification. I won't go through all the details right now, but they deal with stiffness, uniformity, permanent deformation, those tenets I talked about earlier. There's also an element here that allows you to quickly get information on what materials, call that material vision, what materials are being compacted, and then we have control charts with a number of different parameters that are being used. After years of figuring out how to process data, spreadsheets, we've come up with automated PDF generation process that outputs color-coded maps to users, and that information then is shared using some automated alert systems that the agency or contractor sets up so that the information flows when it's needed. Okay. And I'm going to jump over. Tell me if you see the data on the screen.
Yeah, there's a map, but you're
kind of blue. Okay. So behind all of this, what we call our dashboard system are some analytic tools that are used to process, playback, and visualize the data. This is just an example one that I brought up here. I'll just show you the normal stuff. We call these the polygons. There's different ways for managing and processing the data. One is in a grid pattern and another is in a polygon. And the grid pattern approach is really great for data sharing. Polygon is a little bit better for visualization. That's just what I'm showing here, just some of the compaction output. So there's the normal stuff, passes, So maybe you want to look at 1 pass, 2 passes. Back this off. We'll go with 1 pass. Green shows where there's 2 passes. Blue, so this one didn't have a lot of passes, but you get the idea on how that works. And then we've got a feature, and this is really important for pavement foundation and also inspection. Where do you do testing to verify quality? And that we've come up with a technique that takes the data and uses some statistical analysis to render a new data set. And let me shrink that down just a little bit. And the idea is that we might only be interested to know where there's sort of substandard conditions. Sometimes, though, we might want to know not just where there's what we'll call soft spots, those would be the red areas, but we also might want to know where there are stiff spots, because for pavement applications, when you have non-uniformity transitions from high stiffness to low stiffness, you want to know where those are at. Sometimes it may seem counterintuitive, but these high stiffness areas can be problematic, just like a low stiffness area. So there's just different approaches for looking at that data, extracting it, finding out where there's areas of interest to do testing. And we're now using this information as our process to do what I call intelligent inspection, which is let's go to these areas and do DCPs or LWDs or other tests to figure out what's going on. So that's kind of behind the scenes how some of this stuff gets done. Now I'm going to come back to are we back to the report results?
We're not quite there yet. Blank.
No?
There you go. Now we see a screen that says VIC report.
Okay. All right, thanks. So what I thought I would do now with the time that we have left is just walk through, do this pretty quickly because there's a lot of information, just some of the things that we saw in mapping the resilient modulus results for each of the different sections. So this was the 124, 424. And I'll scroll through this, show a few pictures. So this was aggregate base over sandy subgrade. This was the first section on the west end that we had to map. This is looking east. And it was really stable, very stiff, really looked like a nice section. This had concrete pavement over the top of it. So the mapping results here, this is the 30 psi cyclic stress resilient modulus. In the header, you can see that the mean value is about 50 KSI. Coefficient of variation is 26%. In the bottom left, this section depicts what was mapped out. So that was the class 5 over the sand subgrade. And then over on the right, there's a color-coded scale showing red as soft, green and blue is pretty good, and then the purple color is very stiff. So this section was pretty stiff. Now I'm going to transition to the next plot. And this is the same result, but at 10 psi. So it looks very similar. And as I go through these, we'll be switching between, we just picked 30 psi and 10 psi for purposes of showing these maps. I'll flip through those as we go forward. Now this plot in the lower left, you'll see that we're only showing the class 5 aggregate base. We've grayed out the subgrade layer. So as I'm going through these quickly, you can get an idea for what we're showing. So this happens to be just the base layer modulus. So if I go back a couple. This is composite. And then as I go forward, this is base at 10 psi, base at 30 psi. Now this is the subgrade layer. And the mean value was about 40 KSI. So of all the sections, this came back showing that this subgrade layer was one of the stiffer ones that we had to work with out there. It was much stiffer in comparison to some of the clay loam and certainly the wetted section that we had. And then 30 PSI, there wasn't very much of a change, stiffness. Okay, so I hope that's clear. I'm just going to back up here, just go through the maps one more time. Everything's pretty stiff. And 138. So this was quite a bit different foundation characteristics, and this was a little challenging to map because we had all these grade sticks we had to drive around. That's why some of the maps look a little funny, because I was trying to do the slalom through the grade sticks there. There's another image of it. You could see in the foreground there's some little bit of rutting. We could see just with our eyes that this was softer compared to the other section. And this was a mixture of subgrade and base material. And modulus was about 8 KSI, 10 PSI. And as the stress goes up at 30 PSI, the stiffness goes down to 6 KSI. And that's characteristic of finer grain materials. The higher the stress, the lower the resilient modulus. Typically the opposite for granular materials. And then this is cell 38. There was some additional compaction, trimming, some rework that was done. And then we had the chance to remap that. Saw a little bit of improvement up to 10 KSI. Higher stress, it still goes down, 8 KSI. And just continuing to move on here. Cell 39 was clay loam. That was worked. Some of this material had to be imported. It was worked in, compacted. We had a chance to map that out, about 9 KSI, 10 PSI, and then drops down a little bit with higher stress. And then this is after placement of the recycled aggregate base, compacted, trimmed, looking east. Over to the right, you can see I-94. Map that out. Saw a little bit of improvement, not a lot. In the composite response, the underlying subgrade layer has a huge influence on the composite resilient modulus. So even after placement of the aggregate base, we're still really just seeing a reflection of the subgrade layer beneath that. But then when we isolate it to just the base layer output, it was about 12 KSI and then 10 KSI for 30 PSI. And then mapping of that subgrade beneath there, 5 KSI, 4 KSI, was pretty soft. Right. 185, this is where we had the opportunity to do some of the calibration testing. So we had 12 points that we were able to do testing. This was one of them on 185. 12 inches of recycled concrete aggregate base, sand subgrade. We had 2 test locations, 11 and 12, as calibration points there. So this was good because it was a stiff area, gave us an opportunity to get calibration on some stiff material. Composite numbers here at 10 and 30 PSI. Base layer, about 40 KSI, and then 45 at 30 PSI. So here we see the base layer stiffness going up with increase in stress, as we would expect. And then the subgrade beneath here was very stiff at both stress levels. So that same subgrade, again, was quite a bit stiffer than the clay subgrade. Just to illustrate what we're measuring with that plate load test system is this response of resilient modulus as a function of cyclic stress. We're also measuring permanent deformation, which was quite low at this test location. That's what's shown on the right, how much permanent and also recoverable deformation that we're getting. And then we break it apart into base and subgrade. And what was interesting here is that the measurements were showing that sand subgrade had a very similar stiffness to that recycled concrete base over the top. And that was pretty interesting here. Again, just showing us that sand subgrade compacted, confined is pretty stiff, about 25,000 PSI for resilient modulus. This was another point adjacent to it, similar kind of response with increasing stress, higher modulus. This is 189 looking to the west, and then 188 in the background. Had a couple additional calibration points there, kind of intermediate stiffness. Here we had the 12-inch recycled aggregate, 3.5 inches common borrow, and then the clay subgrade beneath it. Just scroll through the maps for the base. And the subgrade here was about 15 KSI to 12 KSI at 30 PSI. So here, if you look at the resilient modulus response as a function of stress, you see that the resilient modulus is decreasing with increasing stress. So that's quite a bit different than I had showed you earlier in that stiffer section where we saw higher modulus values with increasing stress. Also, we had a little bit more permanent deformation occurring in this section compared to the other. And then this is comparing the aggregate base layers modulus relative to the subgrade. So it's interesting about that clay subgrade response is that as the stress goes up, you see a significant reduction in modulus. So it's essentially a kind of a strain softening kind of behavior. The modulus goes down as the stress goes up. That's why you want to have a base material. You want to help keep the stresses at that subgrade level low. These are just a few more of those plots. All right, 133. This one was pretty interesting because we had the opportunity to map the existing base material, and it was I think it was about 1,500 feet long, and it was pretty well intact. And then over the top of this was this cold central plant recycling material. Yeah, it was a real interesting material. The picture at the left here shows me just pushing my thumb into it. This was, I don't know, maybe just a few days after it was placed. And over on the right, I had to drive the roller through it and could actually see, if you look closely, the imprint of the tread on the tire. So it looked really good. It's just almost kind of a rubbery feel to it. It's really interesting material. The map on the base layer was really interesting because it showed this pattern that we didn't see in the other maps, where we could see that there was some stiffness in some areas, the blue areas, but there were still some weak areas in the red. So the coefficient of variation is 35%, a little bit higher than some of the other sections. And then this is after the recycled cold central plant material was put down and had a few days to cure out. Went in and mapped that, and what was interesting here is from a composite standpoint relative to the base layer, we could see some areas that were getting really stiff, like on the west end, but in the middle areas we had some areas that were still quite soft. And this was the only section where we could identify that the surface layer in some areas was weaker than the base layer beneath it. So don't know exactly why, but probably related to the mixture of just the nature of those materials. So we thought that was an interesting outcome from that section. All right. 133 this was earlier mapping on the existing base and then a repeated test on that cold central plat area, just a little bit farther down, more to the east, so similar kind of response. And I'll kind of wrap things up here talking about the section that had the subgrade that was wetted down. And I think the idea here was with that large aggregate to create some softer conditions to see how well that large aggregate thickened base sections would perform, to see if it would overcome weaknesses in the subgrade, which would be pretty valuable to know that information. So that process involved wetting, mixing, and compacting, and there's some nice YouTube videos that NDOT put out describing that process and some of the outcomes. So this is some visual on the preparation. And then placement of that larger aggregate subbase material. And we had the opportunity to do some of the plate testing. So here's the 18-inch large aggregate base section over the soft subgrade. And we had 4 calibration test points in that area. Just how the different layers, this is the base, the subgrade. Looked to us to be a little bit stiffer in the 127, 227 compared to the 128 section. In the lower right, you'll see that red popping up on the subgrade there. But at high stress, we're starting to see that even in the 127, 227, we had soft conditions. Still not quite as soft as in the 128. So when we do the APLT testing, we do in fact see that softer condition. We see more permanent deformation, which is exactly what the maps are telling us. For the subgrade layer, shows up as being very soft relative to the base. So I'll just kind of scroll through those quickly. And then here is the comparison to the 128. Again, large aggregate base over the softer subgrade. Some of the visuals from that. And looking back, everyone noticed there was some pumping of material that was working its way up through that base, and that can happen when you have soft subgrade. And I think that was part of the motivation when these sections were reconstructed, to incorporate geosynthetics in there to help prevent that subgrade from working its way up into the base. See some of the rutting and cracking. So we had the opportunity to map out, do some testing. So the composite values. The base layer was a little stiffer. Subgrade was really soft, especially in that 128 area. So we did testing. It showed, composite stiffness values. If you look at the right here, this black line, you can see permanent deformation's really taken off. Whenever we see that, we know that's going to be problematic for the pavement system, regardless of modulus. It's great to have modulus, but if you have permanent deformation occurring, that means you're going to have set the stage for pavement performance issues. So looking at each layer, the base layer here, which is the orange line, just didn't see any improvement with stress. So the rock was there, but normally we'd like to see the modulus go up with increasing stress, and the wet subgrade, I think, wasn't allowing that to happen here. So here's some pictures after the surface capping material was placed, after the reconstruction. And we had multiple passes here, which was kind of cool. This is pass 1, pass 2, and I'm just going to flip through these. What we noticed right away was, gosh, we're getting some improvement here, like a 15% improvement in stiffness just from adding additional compaction from pass 1 to 2. And then this is at a different stress level, same thing. See a 10 or 15% improvement modulus. Then the base, pass 1 and 2. Then the subgrade, saw some changes there. So some additional pictures here. This is 128, 228, pass 1 and 2. Composite, base layer, subgrade. Still showed it was very soft, especially at the higher stress levels for both pass 1 and 2. We could see some rutting, a little bit of cracking at the surface. And as I mentioned before, these profiles ended up being very similar to what they originally were, but the geosynthetics were incorporated. So here's some pictures of placement of the non-woven triax grid, what it looked like after mapping. We had the opportunity to do plate testing on those sections. And I thought this was kind of interesting that here we're showing in the upper left the triax grid section, triax with fabric, VX with fabric, and then the bottom right, the BX grid. And we tried to look at some of the differences between all those different sections. So that's pass 1 composite, pass 2. So again, we were able to see improvement. We'll just kind of flip back and forth with additional passes. 3 plate test locations. Got up to 4 passes, 5 passes, 6, 7. Went back and did additional plate testing in each of those sections. Here's at 30 psi. It's just showing that it's pretty stiff. Pass 5, 6, 7. We did additional plate testing there. And then here's the base layer results, and you can almost start to see some differences now between the different sections, where we had a little bit stiffer response in the geogrid only in the upper left, and then in the middle with the fabric it was a little bit lower stiffness, pass 1, pass 2, pass 3, pass 4, 5, 6, 7. Again, start to see some differences between the different sections there. This is just the base, 30 psi. And then the subgrade. Subgrade was just soft the whole way through the number of passes, the different stress levels. It was just showing that it was soft as we would have expected. So And then we did the plate load testing and got results somewhat similar to what we expected. Just going to kind of go through those quickly here. I pulled out some of the line plots. So the vertical axis here is resilient modulus, and then we have distance. You can see for the different sections here. It's kind of a tan data point with a black line through this, shows the before reconstruction. And then we have pass 1, 2, and 3, the red, green, and blue after 7 passes. And I thought it was kind of interesting. If you look here at the base layer modulus values, you see improvement in the BX section, in the TX section on the far right and the far left. Not quite as much improvement where the fabric was included in the middle. And I'm saying that based on the difference between the original map and then the after we had additional 6, 7 passes of measurements in there, what the change vertically was in that stiffness. So we're seeing some nice improvement in at least 2 of those sections. Then this is the subgrade. Basically, the subgrade wasn't showing any change at all. It was just soft. So that's what we saw with that data. So that kind of wraps up where we're at with our results to date. All of this will be incorporated into this project report that we're going to get to MnDOT here sometime yet this week. Bob, do we have any time for discussion or questions?
Yeah, we've got about 10 minutes, so anybody who would like to ask a question, please unmute your phone and have at it.
I've got a quick question. This is Venice from Illinois, DOT. Can you hear me?
Yes.
Yes, sir. Yep.
Earlier in cells 127 to 227, you had 18 inches of large aggregate over the soft subgrade. I'm just curious, did you put down the 18 inches all at once, or was it layered?
Yeah. John, do you want to answer that?
Yeah, so half of that, it was done 2 ways there. In half of that cell, it was done in 1 layer, and the other half in two lifts.
Did you notice any difference when you had the 18 inches as opposed to the 2 9-inch layers?
Well, I guess we don't know well yet as far as the results. We're still just compiling the results, so that's don't have an answer yet for that.
Okay.
I have a question. This is Xuntao Dai from MnDOT. Dave, so for this resilient modules mapping, how did you figure out the modules between these points?
How did I figure out the modules between the points from the compaction results?
Yeah.
Yeah. Okay, so basically about every 1 foot or so, it's actually a little bit less than that, we're getting a response from the compaction machine. And we use that response in some data analytics that allow us to calculate the resilient modulus at that point. So every measurement, every 1 foot or so, as that roller moves forward, we're getting a set of data that we then use to calculate resilient modulus. And that calculation is based on our validation using the APLT, the on-site in-situ testing.
Okay.
So once we go through that process, and here we had 12 data points, which for me is about the minimum that I'd like to see as part of that. Prefer about 20, but 12 was pretty good at the site. We ended up getting pretty good correlation results. The idea is that once you have those measurements for these materials, you can plug that into the machine and then output the appropriate value, resilient modulus value.
Okay.
Hey, Dave. This is Pavana. Just wanted to make one comment there. I think in the end we ended up with 21 points because we did 12, and then we had an opportunity to go back to the geosynthetic section, so it ended up being 21 points. Just wanted to clarify that.
That's right. Forgot about the geosynthetic. Thanks.
So the modulus you calculate is assuming the half space to calculate the modulus?
Correct.
Okay. All right, thanks.
On the comment on 128, section 127, 227, if you flip to the next modulus map, you'll see the divide between 127 and 227. There were some differences in the numbers. I don't think I reported the averages, and I don't, John, maybe you remember off the top of your head. I don't remember which one is one layer versus which one is two layers.
Sorry, I can't remember either. But the bottom line is, these are those. This is where it was split. This cell is half. That 18 inches went in one lift and one half, and two lifts in the other. So, between the report that Dave has and his team has produced for us, and then our original work plan, this will be sorted out over the next several months.
Okay. If you know which one it is, then we certainly can. Right now, I think in our report we combined the two sections to report the averages and the other statistics. We certainly can split them.
Yeah, we can do that. Oh, yep, let's do that.
Yeah. That's all I had, Dave. Sorry to interrupt.
No problem. Thanks.
So are there any other questions for this, or should we wrap this up?
This is Heather from Illinois. Just one quick question. Was it recycled asphalt pavement and not cold plant processing for that one section?
Yeah, this is something here.
Yeah. Is that actually what is recycled asphalt pavement wrap?
Actually not. Dave, besides, this is John here in Minnesota again. So Dave White and his team were able to, beyond the geotechnical sections, there's other cells out there, one of which was actually this cold central plant that was separate completely from our geotechnical sections.
Oh, okay. Thank you, John.
Is that it for questions? If so, thank you very much for Dave for this presentation, and thanks to everybody who showed up today. Thanks.